Hello, future math for elementary school teachers. This is Gary Parker, your coach this term. Let's get started. So, we got our Canvas course like before. I set this one up a little bit different, but kind of the same. Check out the introduction. I posted a video there from the other day. Information about workbook activities here, a daily calendar, which we'll try to keep. We'll see how snow days keep us. See, everybody pretty much did the about you, except one person. You know who you are. If you could do that soon. And let's do some math. So to get to stuff in this course, you can use the links down here to get to the homework, to get to the ebook, calendar, or you can go to MyLab Mastering and you can get the stuff through the student links. You won't see the instructor links. The assignments that are listed in the assignment section are only to get things into the gradebook from my math lab, but you can't actually get to the assignments from the assignments page, so you can pretty much ignore that. However, further down here, I have the activities. I should move those up top. Oh, get there. Okay, activities, there we go. And so I want you to get started on the Chapter 4 activities ASAP. I'll take a look at a couple of those in this recording of the next one. All right, let's see, anything else here interesting? The syllabus is in here, I think. Did I remember to put the syllabus in here? I did. Oh, good. Let's see, did I get the final exam date right in here? March 22nd. Hey, I think I got that right too. All right, syllabus looks good. Things aren't too much different from last term. In the, let's see, course home, activities, you have the workbook, you're golden. If not, I have a link to Chapter 4 workbook here. It takes you to this page. We'll take a look at that in a minute. The main link to my math lab takes you to this opening page. There's some homework due soon. My hope is that you will, on your own, do most of Chapter 4 prior to me seeing you again on Wednesday, again, for the first time. But even though school is not meeting on campus, we still have work to do. So the ebook, if you have that, is going to be greatly useful. And so please be reading this. It's very important. I will go over most of the stuff in here, but slightly different. We're going to start off with divisibility, and then we're going to jump into primes and composite numbers, greatest common divisors. So I'm going to kind of work backwards on that stuff. So what is number theory? Why do we need it? Well, there's lots of reasons. Number theory is mainly the theory of whole numbers, but it branches into all kinds of other areas. So an example of why we might need number theory. Suppose we had, how about 5/12 plus maybe 4/15. To add fractions, you have to have a common denominator. Why? We'll get to that soon, but I do. Typically what we do is we look at the denominators, 12 and 15, and we try to find the lowest common multiple of the two of them. Since they're denominators, that's the lowest common denominator. So what I'm doing here is what's called the LCD algorithm. So I have to find a number that both 12 and 15 go into, and it's the smallest possible number that they both go into. A couple of ways to do that. One way is to get the prime factorizations of each of these numbers. And so I could make a factor tree for 12. Let's see, 2 goes into 12 6 times, and 2 goes into 6 3 times. So 12 is equal to 2 squared times 3. And then I can do the same thing for 15. 2 doesn't go in, but 3 does 5 times. So 15 is equal to 3 times 5. And if I'm looking for a multiple of these numbers, for 12 to go into the number, it has to have a factor of 2 squared and a factor of 3, because that is the essence of 12. As far as 15 is concerned, it has to have a factor of 3, and a factor of 5. Right? 3 and 5. Well, I already have a factor of 3 and I'm building the LCM. I just need to add that factor of 5 in. And so my belief is that 2 squared times 3 times 5 is the LCM. So let's see, what would that be? 12 times 5 is 60, pretty sure. So I think the smallest possible denominator I could have is 60. All right, so number theory, how to find divisors, particularly prime divisors, how to find multiples of a number, particularly lowest common multiple. It's pretty complicated stuff. 12 and 50 not very big numbers either. Anyway, and I got to come back over here to the 12/15ths, and I have to rewrite it with a common denominator. So I need to know how many 60ths is 5/12ths, and I need to know how many 60ths is 4/15ths. Boy, well, that means I got to know how many times 12 goes into 60. Okay, well, if I look back at the divisors over here, I know 12 is that stuff right there. So the only thing missing is the 5. So that means I must have to multiply the number over here by 5 top and bottom. So the 5 times 5 means 25 60ths is the same as 5/12ths. As far as the 15ths is concerned, when I look at the LCM factors, 15 are those factors right there. So 2 squared is the only thing missing. So 15 must go into 64 times. So then I'm going to have to multiply that in. And so I'll have to do 4, oops, that's not a pen. I'll have to go 4 times the denominator and 4 times the numerator to build that up. So that means I get, what, 16 60ths. Now we worked hard there to find the lowest common denominator in order to add these two fractions. And so now 60ths describes what we have. I have 25 of them and 16 of them, so altogether, what's that? 30, 41 of them? All right. Yeah. Okay, so then I have to ask myself, is this guy right here reduced? That is, are there any factors that both 41 and 60 have in common? Well, I know the factors of 60, I have them written above, but I don't know the factors of 41. So then I have to go over here and work that out. What numbers go into 41? Well, let's see, 2 doesn't. Does 3? There's a trick with 3. For 3, it turns out that if you add the digits for plus 1, if the result is divisible by 3, the number was divisible by 3. We'll talk more about that later. 3 doesn't go into 5, so 3 does not go into 41. See, 2, 3. I don't need to check 4 because 2 didn't go in, so no even number can divide 41. We'll talk more about that fact in a minute. Let's see, what would be next? 5. I have to check 5. Well, it doesn't end in a 5 or a 0. That's kind of a cool trick, so 5 doesn't go in. Let's see, by the same logic that 4 didn't work, 6 won't work. 7, let's see, 7 times 6 is 42. That's too close. 7 won't work. When do I stop looking? Okay, I'm starting to lose hope here. I'm just going to guess it's not reduced because I'm running out of energy. So let's just say that's the final answer. Pray I got it right. 41 over 60. So all of the work we did to add those fractions, to figure out what the denominator should be, to figure out how to adjust the numerators, and to figure out how to clean it up, that's all number theory. We're going to break apart some of those ideas in chapter 4 so that we can use them in chapter 6 when we get into working with fractions. All right, so what kinds of things do we have to be aware of? Let's see, I'm not ready for the factor game yet. Let's get a new page. Square paper. Thank you very much. Okay. So first type of number theory we're going to take a look at is divisibility. So divisibility means, for example, 4 divides 12. means that when I try to take 4 into 12, I find that there's no remainder. I think, well, what times 4 is 12? I'm pretty sure it's 3. Yes, 3 times 4 is 12. Subtract, no remainder. Okay. So divisibility, one way to think about it is we have no remainder upon division. Another way to think about it, about doing that division problem, one way to think about division is what do I multiply by? 4 divides 12 if I can find a number to multiply to get 12. And if that number exists, then I can say 4 divides 12. And notation for 4 divides 12, and the way I would write that would be 4, 12. Okay. On the other hand, 4 does not divide through it, say 15. So that's the shorthand for 4 does not divide 15. There is no whole number I can multiply by 4 to get 15. Alternatively, if we divide 4 into 15, 4 times 4 is 16, that's too big, so we would have to choose 3, in which case we subtract and get a remainder of 3. So since the remainder is not 0, it's 3, 4 does not divide 15. All right, so that's the idea of divisibility. Two ways to think about it. One number is a multiple of the other, or upon dividing, we get no remainder. Page. Okay. Now, it turns out there's a whole lot of interesting things that happen with divisibility, some properties that are kind of true in general. So, for example, I know that 4 divides 12, and I know that 4 divides 20. And so that implies that 4 will divide 12 plus 20. So 4 goes into 12 with no remainder, 4 goes into 20 with no remainder plus no remainder is still no remainder. Okay. Other way to think about that is 12 is equal to 3 times 4, 20 is 5 times 4, and those 4s divide out. And so here we can see we can rewrite the right side as a multiple of 4, which is what divisibility means. Okay? And so it turns out that's true in general. If some number d for divisor divides a number a, and d divides some other number b, well, that implies always, let's right underneath, that d will divide a plus b. Now, addition and subtraction aren't too much different theoretically. Physically they are, and so it turns out subtraction works the same way. However, what if we try some other things? Like, what about a situation where, let's see, d divides a, and suppose that d does not divide b. That means there's a remainder for the second one. So then the question would be, what can we conclude about d dividing a plus b? So here we would have no remainder. Here we have some remainder, and no remainder plus remainder is a remainder. So that means d shouldn't divide that sum in general. And so if we try an example of that, let's suppose that 4 divides 12, and 4 does not divide 10. All right, we get a remainder of what, 2 there? So what's going to happen when we take a look at 4 dividing 10 plus 12, or 22. Well, guess what? It doesn't divide 22, and the cool thing is the remainder here matches the remainder over there. Another cute thing about the remainder. Ooh, I got an idea. Check this out. I usually give extra credit, but find me a word synonymous with remainder. And I have no idea if I'm spelling synonymous right. Close enough. It's phonetically right. Word synonymous with remainder. Remainder. A hint, the one I'm looking for starts with an M. Come back to me next class with that. All right, let's take a look a little bit more with this. Page. All right. What about if we say, all right, let's suppose D does not divide A and D does not divide B. What happens then? What can we conclude about D question mark A plus B? And so we might say, okay, well, let's just pick an example. For example, I don't know what. Let's stick with 4. It's a fun number. We know 4 does not divide 10. And let's see, we know 4 does not divide 9. And then we also know 4 does not divide 19. Okay, now just because we found an example that shows it to be true doesn't mean it's always going to be true. You need a chain of reasoning to prove something like that. But to prove something is false, all you need is one example showing it's false. I'm just going to try that again. Let's see. Let's see. 4 does not divide 10, and 4 does not divide 2. Too small. However, I guess the implies is kind of useless here. Let's take that out of there. What can I say about 4? And 10 plus 2 is 12. Oh, crap. It does divide it. Okay. So sometimes I get lucky, and the 2 remainders I end up with, like here, the remainder is 2, and here the remainder is 2. 2 plus 2 is a remainder of 4, but 4 goes into 4. Okay. Up here with 19, I had, let's see, a remainder of 2, and here I have a remainder of what? 1. 2 and 1 is 3. And let's see, 4 times 4 is 16. Remainder is 3. Notice that the sum of the remainders in the beginning match the remainder at the end. So sometimes when we don't have divisibility action going on, the remainders can combine to make divisibility happen. What's the moral of this story? The moral of the story is if D does not divide A and D does not divide B, then we can make no conclusion. We know nothing. And it's always good to know what you know and what you don't know. Right? We don't know anything about that one like that. So there are these generalizations we can make. Those are called theorems usually in math. And sometimes you don't get anywhere with a given set of premises. These are our premises. We can make no conclusion there. So those are some important rules to divisibility. Some other things to know about divisibility are just the relationship between multiples and divisors. So let's pick on the number 12, for example. Okay. So 12 has divisors. Color. 12 also has multiples. Divisors of 12 are things that divide 12 that go into 12 with no remainder. Well, let's see, let's list those. Well, 1 goes into 12, and Oops, wrong color. Let's make the divisors green. 1 goes into 12. Let's see what else. 2 goes into 12. 3 goes into 12. 4 goes into 12. 5 doesn't. 6 does. 7 doesn't. 8 doesn't. 9 doesn't. 10 doesn't. 11 doesn't. Oh, 12 goes into 12. They're the divisors of 12. They form a set. Multiples of 12, let's see, that would be 1 times 12, and 2 times 12, and 3 times 12. And we can just keep doing this all day. There's a whole bunch of them. And eventually we'll find like 100 times 12. Okay. These go on forever. Oops, I'm making the wrong color, didn't I? Darn it. My math is not color coordinated. Let's see if we can fix that. You guys need to be blue. Is that the right color blue? Close enough. That's better. Oops, they good. All right, so the multiples form a set too. And that set, unfortunately, or fortunately, I don't know, depending on your point of view, is infinitely long. It just goes on forever and ever and ever. So there's lots of multiples. Notice the multiples of a number are greater than or equal to the number in question. The divisors, on the other hand, are less than or equal to the number in question. Oops, I put the 12 on the wrong side. Let me just get rid of that. It's in the wrong color too. All right, so the divisors are less than or equal to 12. They're always smaller or equal to. So a number is both a multiple and a divisor of itself. Sometimes with divisors, we talk about proper divisors. Those are the numbers that are strictly less than the number. So the proper divisors are 1, 2, 3, 4, and 6. So those are the proper divisors. All right, so divisors versus multiples. And there's that relationship that goes back and forth. 12, let's say 6 is a divisor of 12, and 12 is a multiple of 6. So we can kind of put things in opposite directions there. Right, so 6 is a divisor. There we go. 12. And if we reverse the numbers, we would have to say 12 is a multiple of 6. Right, divisors versus multiples. If we put two numbers together, they can have common divisors, or they can have common multiples. We'll take a look at that in a minute. As far as divisors go, there are some numbers that are rather boring when it comes to divisors. So for example, what if we looked at the divisors of 13? What number divides 13? Well, we always get 1 into a number. Let's see, 2 doesn't work, 3 doesn't work. Well, 13 is kind of dull. Only 1 and 13 go into it. Numbers that have exactly 2 divisors are special numbers. They're called prime. And we say primes are the building blocks of the whole numbers. So my definition of prime is having exactly 2 distinct or different factors. And often we use the word factor and divisor synonymously. So factor is the same thing as divisor. So primes are special. When we're talking about whole numbers, a number is either prime or it's composite. Composite means more than 2 factors. Can a number have less than 2 factors? Turns out it can. That would be the number 1. Right? 1, is equal to 1 times 1. Those aren't distinct, they're the same factor. So when we break up the counting numbers in terms of divisibility, divisors, we can break them into 3 groups. Either the number is prime, or the number is composite, or it's 1. 1 is neither prime nor composite. It's a weird number. Okay, so we have prime, we have composite. So the study of primes and composites, divisors and multiples are important for a lot of things. Specifically, they're important to fractions and decimals. And so we're going to need them for that. All right, so let's take a look at multiples. New page. In particular, common multiples. So let's see. I had 12 before, and I had 15. And multiples of 12, starting at 12, they would be like 12, and 24, and 36, 48, what comes next? 60, and then 72, and then 4, 96, and they just keep on going, yada, 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 all the way down the line. And then, excuse me, we have the multiples of 15. 1 times 15, and 2 times 15, and 3 times 15, 4 times 15, and they just keep going. 60, what would be next? 75, 90, 105, 20. Now notice that, let's see, do we have common ones? I think if I keep going with 12, I'll get a common. Let's do a little more work there. Maybe after 96, 108 plus 12 is 120, and they both keep going. And so in this case here, we have a common factor of 60, and we have a common factor of 120. Okay. And we're going to have common multiples, sorry, I said factor. Oops. We're going to have common multiples for ever and ever and ever for 12 and 15. Often what we're interested in is the lowest common multiple. And one way to find the lowest common multiple is to list the multiples of each until you find the first one in common. Sometimes that can take a while. And so we're finding that the lowest common multiple, LCM, and sometimes we'll write parentheses and list the two numbers next to each other. We're finding that that's equal to 60. There are other ways to go about finding the lowest common multiple. One way is with the prime factorization. So let's take a look at that. 12 with a factor tree, more on factor trees in a moment, is equal to 2 squared times 3. 15 is equal to 3 times 5. I'm going to go about it a little bit different this time. I'm trying to find the lowest common multiple based on the prime factorization. Well, if something's a multiple of 15, 15 must divide into it. Well, 15 is made up of 3 times 5, so that means the LCM has to have a factor of 3 and has to have a factor of 5, because that is 15. Then 12 looks at that group of factors and it says, hey, I like that 3, I don't care about the 5, but 12 says you are missing a pair of 2's. So the 12 would add that to it. And then I asked myself, can I afford to get rid of any of those? All right, so what did I grab here? Looking at this, I first grabbed the 3, and then I grabbed the 5, and 12 said you need a 2 squared. If I try to get rid of the 3, both 12 and 15 are unhappy. If I try to get rid of the 5, unhappy again, 15 will be unhappy. And if I try to get rid of either of those 2's, 12 will cry. Say, hey, no, I need that. So to build a common multiple, I have to use the same prime factors as the numbers I start with. And it turns out what I want when I do that is you, and we'll see this as I do more examples, you end up with the highest power of each prime present. That's my claim. I test that claim in a minute. So I think the LCM is the highest power of each prime present. Okay, and so let's see, 3 times 5 is 15, 15 times 4 is 60, which is what we believe it to be earlier. Okay. All right, we'll take a look at another way to get the LCM later. Next, let's go back to divisors. How do you find all the divisors of a number? That can be a lot of work. The easiest way to do it is by looking at pairs of factors. So we call them pair complements. So, for example, when I'm focusing on 12, I would ask myself, well, let's see, what times what equals 12? Well, the simplest thing I could start with would be a 1 times 12. And then I move up and say, okay, does 2 go into 12? Yeah, 2 times 6. Does 3 go into 12? Yeah, 3 times 4. 1, 2, 3. Next I would go for 4, but I've already covered 4. 5 doesn't go into 12. 6 does, I already got that. 7 doesn't, 8 doesn't. So there's going to be a turning point in the list of pairs such that you know you're repeating stuff because you got things on the other side. And then the question comes, when does that turning point happen? Because sometimes it can be a ways down the road. So let's repeat that process with 15. 15 is 1 times 15. We always have that basic one. See, 2 doesn't work, but 3 does times 5. 4 doesn't work. 5 does, I already got that, and so then I'm repeating myself, so I found the turning point there. So I can see that 15 has 4 factors and 12 has 6 factors. Do they have any common factors? Okay, let's see. They have 1. All numbers have 1 in common. What else do they have? They have 3 in common, and that's about it. As far as factors go, or divisors, usually what's of most interest to us is the greatest of the common divisors. And so here, the greatest of the common divisors happens to be 3. And when we look at the prime factorization, it turns out we can tease out the greatest common divisor, greatest common factor. So remember, 12 is equal to 2 squared times 3, and 15 is equal to 3 times 5. And so here, what I want to do is, take a look, what do they have in common? Let's switch highlighters. So let's see, they don't have a 2 in common, but they have a 3 in common. Okay, and that's it. All right, we'll look at a more interesting case in a minute. So the best I can say for the greatest common divisor, sometimes it's called the greatest common factor, oops, that's supposed to be a C, is that it appears to be 3. Now notice something. If I get rid of the highlight over here, put 3 back in, when I selected factors for the lowest common multiple, back at the page here, I selected these green factors over here on the left. And notice that the GCD happens to be that leftover 3. So is there a connection in general between the greatest common divisor and the lowest common multiple? So that's something we'll explore. Another way to go about finding a greatest common divisor is by using what's called the division algorithm. So think back to Math 211 for that. Oops, wrong kind of paper. Again. Wrong paper. Last paper. All right. So the division algorithm. And what the division algorithm said was that, let's see, which number should I use? How about B? If we take B into A, we do that division. We could write it like B goes into A. That implies that there's going to be a number called Q, such that if we take B times Q, and there could be a remainder R, that is going to be equal to A. So other things about this division algorithm, that remainder R has to be less than the divisor B, and it has to be greater than or equal to 0. So it could be 0, but it's got to be less than the divisor. And then Q is just some whole number. It's called the quotient in the remainder. The division algorithm is about quotients and remainders. So for example, if I do something like 15 divided by 4, let's do a different one. Let's do 14 divided by 4. Then I should be able to find a quotient, 4 times 3, and a remainder, such that the remainder is less than the divisor, and that will always equal the numerator. Okay, so that's what the division algorithm says. Now, what I can do is use the division algorithm along with my two numbers. So I was looking at the numbers. I'm trying to find the GCD of 12 and 15. And so what you do is you consider the division problem 15 over 12. 12 goes into 15, you're done. 12 is the GCD. But generally that won't be the case. And so we say, okay, take the big number according to the division algorithm. That should be equal to 12 times some whole number. In this case, that whole number will be 1 plus a remainder of 3. And then what you do is you take your old divisor, make that the new dividend, and you take your new remainder and make that the new divisor. So now I'm going to consider the division problem 12 over 3. And so my 12 jumps up front here. And I say, okay, 12 equals 3 times what? Well, that would be 3 times 4, plus 0 remainder. Once you hit that 0 remainder, that's a big flag. That says, hey, the previous number has to be your GCD. And this process of using the division algorithm to find the GCD is called the Euclidean algorithm for the GCD. Euclidean algorithm. And it's very powerful and very fast. Let's see, algorithm. And so it allows me to quickly, with just a little division, look at two numbers and figure out their GCD. Does it always happen in 2 steps? Answer is no, it doesn't always happen in 2 steps. So let's pick some other numbers to play with. And then let's talk about the activities a little bit. Okay. All right, how about 24 and 18 maybe? Sure. 18. All right, so let's do factor trees on those. 2 goes into 24, and a factor tree is to get the prime factorization. It's 12. 2 goes into 12 times 6. 2 goes into 6 3 times. 18. What do we got? 2, it's even, right? 9 times, it's not even, so we try 3. goes in 3 times. All right, so we got the prime factorizations. 24 is 2 to the 3rd power times 3, and 18 is 2 to the 1st power times 3 squared. All right, so then what I want to do, I'm going to do a couple different things. Go back and think about the LCM of these guys. And the LCM, usually what I do is I pick one of the numbers and say, well, if 24 is going to go into it, it has to have the same prime factorization to start with. So it's got to have 3 2's in there, and it's got to have a 3. And then I let 18 consider that. 18 only needed 1 2. It doesn't care if there's more, but there's not enough 3's for 18, so I have to bump that up to a 3 squared. And so then I wonder, can I remove a 2? And the answer is no, 24 would be unhappy. Could I remove a 3 from the LCM? And the answer is no, because then 18 would be unhappy. So I think I have the smallest group of prime factors that both 12 and 18 will be satisfied with. And let's see, what does that come out to? If I multiply all of that out, I get 8 times 9, the LCM is 72. So my belief is that 72 is the smallest number, such that both 24 divides 72 and 18 divides 72. And that's the LCM. So you could say, in that selection, we chose that group of factors and that group of factors right there to get the LCM. All right, let's take a look at the GCD. So let's pick a new color and come down here. For the GCD of 24 and 18, I consider their prime factorizations again. 24 is 2 cubed times 3, and 18 is 2 times 3 squared. And let's see, common divisors. Well, 2 divides both of them, right? But only 1 2. 2 squared would be too much for the 18, and so would 2 cubed. So the best I can do is say, all right, they have a 2 in common. And then this one has a 3, and this one has a 3 squared. So at most, they have a 3 in common. And so it looks like 6 is the largest number that divides them both. Okay, a 2 and a 3. Now notice when I found the LCM above, the remaining factors up here that I didn't pick were a 3 and a 2. Back to my theory that the factors that the LCM doesn't pick make up the GCD. And we'll take a look at that more later. So we have more evidence toward that theory. We'll talk about how much that makes sense for other numbers later. Taking a look at the Euclidean algorithm, let's see if we can squeeze that in here. The Euclidean algorithm says take the smaller number into the bigger number, so 18 into 24. And so we write that as a product with an addition. So let's say 24 is equal to 18. So let's see, 18 goes into 24 once with a remainder of 6. And then the 18 comes out front, and we ask if 6 goes into 18. Let's see, 6 goes into 18 3 times with no remainder. And so that says the previous remainder has to be the GCD, which we already know. Now this happened in 2 steps again. Sometimes it can take more than 2 steps. But generally the Euclidean algorithm works pretty quickly. So usually within 4 or 5 steps, you'll have the GCD, which is kind of nice. All right, that's a fair amount of math there. So what have we covered here? We've covered some stuff in section 4.1, some stuff in section 4.2 about primes and composites, and some stuff in section 4.3 about divisors and multiples, in particular, greatest common divisor and the lowest common multiple. The activities that you need to work on are activities 2, 3, and 4 in the workbook. you don't have your workbook handy, they are available through this link online. And so activity 2 is called a square experiment. You will need some graph paper to play with that. And here, zoom in on this sucker. Let's see. When I consider rectangular arrays, this array over here is 1 by 3, and this one is 3 by 1. So they are different. And so what we're taking a look at is the number of different ways you can make rectangles given 6 blocks or 5 blocks or 4 blocks. And we're going to make a connection between the number of factors a number has versus the number of different rectangular arrays that you can make. So if you can make a 1 by 6, that means you can make a 6 by 1 and reverse it. All right. However, if you think about 9 for a minute, 9 is 3 by 3. You can't reverse that. It's still 3 by 3. And then you're going to try and answer some questions on those. So do your best, give it a shot, communicate with your classmates about it. So I'm expecting you to be able to complete most of this before our next class, which happens to be, unfortunately, a week from today. All right. Next, we have the factor game, which is a little bit weird. So I'm going to demonstrate how that works. This one you want to try to find somebody to play with. And what you need is a game piece. Actually you need multiple game pieces, and you need some paper clips. And the way it works is on any particular turn, a player either puts down a new paper clip, they take a paper clip off the list, or they move a paper clip. And then you take turns doing that. And the whole point of it, let's see, got it over here, is to try and get places on the board. Okay, so here is that right here. So, for example, I might go first, and I would throw a paper clip down. Let's see, what are the rules say for starting? Let's see, one player places 2 paper clips down. Okay. And then each additional turn, you either do A, B, or C. Put down a new paper clip, pick up a paper clip, or move a paper clip. And you go back and forth. So where the heck did that go? There it is. All right. So I would say, all right, I'm going to throw a paper clip on the 2. And I'm going to throw another paper clip on the 3. So that means I would put my game piece, let's suppose I'm pink, on the 6. Okay, so then it's your turn, and you want to throw it on a paper clip, and you think, well, let's see, if I threw down a paper clip on 5, 2 times 3 times 5 would be 30, I could get 30. So you say, okay, I'm going to throw a paper clip down on the 5, in which case you get to put your game piece, say you're green, on the 30. And they say, okay, that's cool. So, and we're just trying to get control of the board. So let's see, what could I do there? I could throw down another paper clip. So my paper clips are blue on the 3, in which case that would be 30 times 3. I just got 90. And so you want to try to find someone to play this with. You could play with yourself, have a split personality. I like me here. And then maybe it's your turn next, and you say, well, let's see, I'm going to move one of Gary's paper clips. Oh, shit, what happened? Ooh, that was bizarre. Huh. Can I move something? Ooh. Sorry, this is a new tool for me. I have no idea what's going on there. That's kind of cool, though. Let's try this button again. Okay. Oh, it's not going to want to move. All right. Anyway, that's not going well for me. I have a pointer here somewhere. Anyway, I can't figure out how my whiteboard works here. I would like to move, say, one of the paper clips on the 3 over to the 2. That would give me 2 squared, which is 4, times 3 is 12, times 5 would be 60. So that means on that turn, by moving a paper clip from the 3 to the 2, the other person would be able to select 60. And you just keep going back and forth like that, either moving a paper clip, removing a paper clip, or adding a new paper clip. to try and use the factors 2, 3, and 5 to build a prime factorization that leads to one of the numbers on the board. It was just a fun game playing around with the idea of prime factorization and shifting those factors about. So please give that a try soon. All right, other games we have to play here. Again, prime factorization tree, get some practice in that there. This one is wicked fun. Give it a try. What you're going to do is you're going to color in on this board on the corners. If something is a multiple of 2, it gets colored, what color? 2 is orange, and then 3 is blue, 5 is green, and 7 is yellow. And so you color the corresponding corner, upper left, upper right, lower left, lower right, going around the board. And if something gets colored, it falls through the sieve. So a sieve, like as a colander, right, you're doing pasta. So we're going to let some numbers fall through. When we're done coloring in things for 2, 3, 5, or 7, any number that does not have a colored corner should be a prime number. So what should be left here are numbers that are prime. And then we'll color them in something else. I think it's, what color do we color those in? Oh, I gotta forget something wrong. Okay, orange is the color of stuff that stays behind. Oh, 2 is red. Okay, corner red for 2. So give that a try. Last couple of times I did this, I made mistakes and had to redo it a couple of times. But you're going to get a beautiful color pattern, and we'll talk about that later. Some questions to answer here. And let's see, what's number 5? Tiling with squares. This one is, again, where you're going to need graph paper. And this one right here is playing around with the idea of GCD by looking at common tiles. So give that a shot. So try all of these this week and this weekend, and then we'll answer questions on them next Wednesday. So we're getting a rough deal this year because, let's see, we have 2 snow days, missed Monday and Wednesday. Martin Luther King Day is the following Monday, so I don't get to see you all until Wednesday. So let's hope we get to see each other then. So please contact me with any questions, and I think I'll add a discussion forum here so people can post questions about homework or activities. So it's general homework. Let's call it general questions. Okay. And let's see, allow threaded replies. So that means somebody can post and you can reply to their post. And this is not graded. We don't need to worry about liking them. Save and publish. Okay, so we now have a discussion forum here where you can hit the reply button and you can ask a question about homework or something in the book or one of the activities, and somebody else or me can reply to it. So have a good day, do good math, enjoy that snow, drive safely, all that stuff. I hope to see you all soon. Take care.